Let's see what is our third question for the day. Okay, so our third question is again, it's related to SVM, support vector machine, and it is called what is kernel and what is kernel trick in SVM. It's also a very fundamental question, so let's try to understand what is kernel and what is kernel trick. Okay, now what is kernel? So kernel function, actually kernel is a short of kernel function, or kernel trick is referring to the same thing in SVM or support vector machine, right? What essentially it is meaning is that you operate in a high dimensional feature space without explicitly computing the coordinates of the data in that space. Let's try to break it down. This is what kernel or kernel trick. So kernel is nothing but a function which lets you calculate a dot product of two vectors in a lower dimension feature space, map it to higher dimension feature space, and calculate that dot product without actually transferring this data to a higher space. Let's again let's try to understand this with an example also over here. Okay, so let's say in this particular case I have two data points, okay, my x1 and x2, and this is in a two-dimensional space. If let's say I have to calculate the dot product of this, what will be my dot product? This is my x1 vector, this is my x2 vector, right? My x1 dot x2 will be a scalar quantity, correct? Dot product is always a scalar quantity, correct? And my x1 x2 is nothing but my x1, you project this is the angle theta, so my x1 norm into x2 norm into cos theta is that value, right? The dot product essentially represents the projection of one vector onto another and the length of that, right? This is what the dot product means. Now let's see, for some reason in SVM we have to do this projection into a higher dimensional space. Why we are doing into a high projection into a higher dimensional space? Because in this dimension these data are not linearly separable. If the data is not linearly separable, in a higher dimension maybe the data is linearly separable, and that's where we use this kernel trick. So what we are trying to do, we are trying to map x1 into a higher dimensional space. Let's say this dimension here, it is 2 dimension. From 2 dimension we are going to 10 dimension. Again here from 2 dimension we are going to 10 dimension. What is this kernel trick is that you, and this thing is mapped, let's say x10 and this thing is mapped to x10 in a 10th dimension, in a 10 dimension feature space. This is the mapping, okay? So in 10 dimension feature space, my kernel is a function which will calculate the dot product between these two vectors without actually doing this particular transformation. You understand? Without doing this particular transformation of the individual vectors to a higher dimension space, I'm still able to calculate the dot product in a higher dimension space. That's why the kernel, or that is what essentially the kernel trick is. Okay. Okay, so friends, I hope that part is understood. Now what I have done is I have written it down over here, but essentially this is what a kernel trick is. And why we are doing it? Because to transfer this to this is a very computationally intensive task. Okay, to transfer from here to here, it's a very computationally intensive task. Okay, or from x2 to x10 it's very computationally expensive. But this particular operation, right, is easy. And ultimately what is our goal as part of SVM? To find a decision boundary, we needed the similarity. The dot product is also called similarity. We needed the pairwise similarity of all the data points in a higher dimensional space. That's what we wanted, right? So if our need is still a scalar quantity, at the end of the day, in a n dimension, in a higher dimension feature space, right, we are calculating the dot product, which is a scalar quantity, right? That is our aim. We ultimately want a scalar quantity. So there is no point of calculating this to this, right? And that's what the kernel function or kernel trick is. In case of, let's say, friends, you assume that if you do the feature engineering, right, sometimes you have to do the data transformation as part of feature engineering. In feature engineering is different than kernel trick, because we are actually transforming all the data points into another feature dimension space, right? But in case of kernel trick, we are not doing. Again, over here I have a YouTube video and a LinkedIn post also, which clearly says that what it is. Let me just quickly go over it, right? This is my LinkedIn post, which I have posted some days back around the kernel trick. You can take a look, and here I have explained in detail that what is this trick, right? So you assume that XY, this is my original feature dimension, 3 dimensions, okay? X1, X2, X3, Y1, Y2, Y3. And I am porting it to a 9-dimensional feature space, right? A 9-dimensional feature space. And here I have shown that how, if you do a kernel trick, without kernel trick, what you will do? You will do the feature mapping, okay? So you'll need these many multiplications for y feature or y vector. Again, you will do this, and then you will calculate the dot product. Ultimately, you are going to do these many operations to arrive at what? A scalar quantity, which is 1024 in this case. What you are doing? You are doing 27 multiplication and 8 additions to arrive without kernel trick. In this particular case, what we are doing? We are actually transforming the data. But with kernel trick, if we have to do, what we'll do? This is my original vector x and y, right? What I did was over here, and this, if you see, with kernel trick, my computation has significantly come down. It is only 4 multiplications and 3 additions, okay? So this is what the kernel trick is all about. I'm creating the dot product in lower dimension, squaring it, I'm arriving at the same number, okay? This also, I have created a small video on my SVM playlist. Let me see, where is SVM playlist? Okay, so yeah, kernel trick. The video number 2 of the support vector machine deals with this kernel trick. And if you need a video explanation of this, that's where you can find it. Okay. So friends, I hope that part is clear.